When I first moved back to Canada, I started many little projects and a lot of them didn't get finished. This is actually one of them that I've been toying with again. And what it basically is half of a EPS power unit. So what is that really? Well, it's basically a motor controller and some circuitry to interface to the motor, but also with a microcontroller that's also wireless. So what I wanted to do is basically make a gravel EPS group set. And that would entail having the motor controller, a battery, and some way of talking to it. So either run wires straight back to it or wireless, or in my case, I wanted to have the option of both. And then this board has a few mistakes and a few missing components, but it in theory worked. I had it hooked up, but I never really finished the programming and I didn't really like where I was going with the design. The battery is a bit of a painful problem, because with the Campagnolo, it's actually 3 cells. So it's around 10.8 to 12.6 volts, which is great because they are using a 12-volt motor and because of some of their design with their gearbox and their linear actuator, which is very clever. It tends to be inefficient, so higher voltage usually gives a higher efficiency motor, and that means higher voltage. That leads us to another problem, which is charging. While good, and though everyone hates this connector, is a bit of a big chungus boy, but it can accept AC and DC. Well, they were thinking about racing and charging in team cars and stuff like that. So it can take 100 to 240 volts AC. So that's worldwide market. It converts that to DC, probably around 15 volts, but it can also take 12 volts DC, and even though that's not enough to charge, so it has to boost that up to, again, probably around 15 volts. And then it can use your standard lithium constant current, and then constant voltage charging, and then stops charging once it reaches the 4.2 volts with a sufficiently low current. But Shimano has a much smaller solution that is a bit more universal. So they take in USB, this USB micro, and they output their 8.4 volts because they only use 2 cells, different gearbox, different setup, different motor powers, different shifting force. Their system takes USB at 5 volts, but because the system needs 8.4 volts, it has to boost it up using a DC to DC converter and then into a constant current, constant voltage charger. That means that even at 5 volts and 1 amp, then you only get 0.4 amps charging, and these cells are generally around 800 milliamps, so at least 2.5 hours to charge. It's a bit slow. I used basically the same idea on the microcharger, and with the microcharger, it's all the same parts, USB, DC to DC, but I boost to like 13 or 14 volts, and then I have the charger. All of these are okay solutions, but for me to package 3 cells on a derailleur with a circuit board and stuff, that gets annoying. I would also want to add things like balanced circuit in order to maintain those, especially because the cells are smaller. There's going to be more potential for them to get unbalanced. They'll need more charge cycles. So there is a lot going on to try and minimize this. USB-C power delivery spec allows me to get higher voltages, so I could ditch the DC to DC converter. However, that would require me to only use things that were at least 45 watt capable, and even things like the new MacBook Air only comes with a 30 watt charger and can't hit the voltages required for me to delete that. But what if I did something different? What if I, instead of having the boost in the charger, which is allow you to make a small, efficient boost, what if I had to have a really big boost? If I use 1 cell, I can use simpler chargers that run on 5 volt USB, but I have to boost that up to about 12 volts, and that is a bit tough. So you need a big boost converter. But the interesting thing is trying to size the batteries, it's much more space efficient to have a big boost converter and a single bigger cell than having to have multiple cells and all the associated circuitry. Now, this is definitely not how everyone in the industry has done it. FSA didn't do it this way. SRAM doesn't do it this way. Shimano doesn't do it this way. I think they all use 2 cells in series, and I don't know what SRAM's balancing or FSA's balancing situation, but Shimano does not have a balancing circuit. And the EPS decided to go 3 cell, and they also don't have a balancing circuit. So no one in the industry is doing this. There is probably a reason. I'm still going to investigate. What am I going to do? Well, I've got a really good and partially available boost converter that uses a really big inductor and some really big capacitors so that I can see, I'm going to do a side-by-side of the performance. And that's what we're really trying to see is, can I do this without losing any measurable performance or any significant performance of the derailleur? So let's take a look at what I've got set up for that. So in here, we've got my spare EPS group set. Except this is the inside of a power unit. No battery. Well, actually, I've got the battery. It's right here. And not in great spec. 3.8, 7.86. It's going to read wah wah wah. So you can't easily see how much current because it's going so fast that by the time it responds, it's already done shifting. So what we need is a way of measuring both the voltage at the motor, but it would be also nice to measure the current at the motor. Basically all we're doing is motor current should go in through one side, or it can return actually, and we have this 10 milliohm resistor. These guys are to sense in an oscilloscope. This is the motor, so it goes up and through and then back out. And then we're just going to plug that in line with the derailleur. So I've had a few failures. Measuring across the sense resistor didn't work out very well, so I tried replacing it with a larger one, and that worked a little bit better, but there wasn't enough resolution on the oscilloscope. Built a differential amplifier, but one of the problems I didn't think about was if I connect their grounds together, then the voltage through the resistor is going to be 12 volts, and this op amp is only about 5 volt tolerant. So it didn't look like it burned out, but it would rail a lot, and I got weird results, and it kept pulling that voltage high. So one of the things about this little guy is that these controllers are MC33926, and unlike a lot of motor controllers, these ones seem to have a built-in current mirror in order to measure current, instead of a lot of them use like my design of this board here, it uses shunt resistors after the low side FETs, and you can measure across them. So they have to dump current into a resistor. So, and I can measure the voltage. So that should allow us to get some good readings on the oscilloscope. What we've got here is yellow is the voltage to the motor. Blue is going to be the current. Every 1 volt relates to 1.5 amps. Shift. And now we can, so you can see here that we're peaking, this is 0, 1 division, 2 divisions. We're peaking at our 1.7 volts and correlating that, that's about 2.2, 2.4 amps. And then it quickly drops off. So each of these is 10 milliseconds. So by 10 milliseconds, we're down to 1.5. By 20 milliseconds, we're under an amp. By 30 milliseconds, or 0.7 of an amp maybe. So we complete the shift. If we run the cursor, it's completing the shift in about 70 milliseconds. But let's give it some load. So I'm just going to hold it down with my finger. Ooh. Now it took longer and it drew more current. You notice our current is much more in line of almost an amp to 1.5, probably 1.2 amps, I'm going to guess. So with that load on it, we took 126 milliseconds. We almost doubled the time, and 1.5 amps almost continuously. So I'm going to set the benchmark currently as this. We know what that is, and it's the low shift. What we have to do now is get that data out. So I'm going to save that out. What we've got here is a dev kit for a 10 to like 15 amp boost converter. This chip here is actually the boost with the built-in switch. It's synchronous, so this is very high efficiency. This is a huge capacitor. This is your output caps. This is a PFET. There's a built-in PFET driver, so you can do a high side switch to enable or disable the output with this enable high-low. And because I don't have any good clips for hooking on to any of this stuff, some ghetto soldering on the back here. So let's set this up, and you know, these wires look awfully small, but I mean, the wires that are being used in the EPS system are also relatively small, so also modified this, that the R1 resistor is changed so that I get about 12 points. 5 volt power supply, set to 3 amps. We'll probably drop that to 4.2 later. That runs up into the dev kit. 12.6 volts. Got my boost over here. Everything else just the same. And let's first see if we can shift. This is the first shift. That's not a good sign. We're not in a great situation, but we'll give it another try. We ramp up, we've got our 12 volts here, and then the boost converter just can't handle it. And then it seems to make its way back up, and then current ramps up as we're trying to drive it as hard as possible. And we keep doing that until we get to a point that the current has dropped below this point, and that point would be about 1.5 amp. I'm running this off of this 18650 cell. This is an LG MJ1 3500 milliamp genuine LG battery. So you can see we've got 2 caps, and this cap's not really going to make much of a difference, so I'll put him over here and discharge him. So I've got 2 big electrolytics onto this. I also have this little guy, which is a 100K resistor, which basically sets the kind of the target frequency. Blue is still current, yellow is voltage. So right now, if I try and shift, it still doesn't work. It dips down. However, I can make it work. So the first thing to do is, so we've got this battery protection charging circuit here, and I've used this on this battery for a while. But there's only so much current, and there's a voltage drop through that FET. So when you do things like you're not supposed to, no, that's the power, you take the ground so that we can now bypass, decrease the resistance from the battery into the board. This is just connected together. Now it works. So the current limit of that protection circuit is much too low. All right. If I adjust my cursors here, you can see that our voltage is dropping to 8.5, 8.6 volts. And now we are taking 87 milliseconds to shift. So that's not as good as we want. What we want is around 70 milliseconds to shift. If I let the frequency drop from around 2 megahertz to 500 kilohertz, it doesn't work anymore. But now let's bypass this wire. Let's shorten this wire effectively by driving that in there. That made a big difference. You can see that our voltage only drops down to 9.9 volts now. So I'll select that again, and our shifting is 74.5. Now, I said it doesn't make a difference. And it really, as far as I can tell, I can't get it to make much of a difference. But these here are 470 microfarads, so I have, in theory, 940 there. So if I add another one, and make sure polarity, because I screwed that up once, that's going to charge up. So 9.9 volts is our low side, drops from 12 during the shift. Our 74.8, let's shift that back down. And we're not making a huge difference. We're not really, so we shaved off a few milliseconds. We haven't shaved off a lot. But what we had, and we haven't done much on the voltage, it's maybe just above 10. So we now have a good amount of capacitance. The capacitors on it were, 10 or 40 microfarads. I tried on the input, that doesn't make a difference. So what I suspect the next step of making a difference here is bigger wires. If we shorten up some of this stuff. But I'm pretty happy right now because I've got almost the normal performance of the derailleur. So now that I've got most of the performance of the derailleur, most people's not going to really notice any of this. So this boost, couple of these really big caps, don't mess up the polarity, high frequency. So even if we drop the frequency, so now we're at around 500 kilohertz, it still will work. No. In fact, it might actually work better. Okay, new learning. Maybe the default was perfectly fine. Yeah, we're seeing a lot actually better performance. So I've been back and forth a couple of times. I'm not 100% sure on that. So now we're actually at, that is very, very close to absolute perfect. Actually, that's happened live. I had thought the higher frequency was better. Let's just take out this one cap again, because he's not, obviously not making great contact. Yeah, still doing pretty good there. So, yeah, that actually might have done even better, but this might be shifting a bit. So there's definitely some variance there. Yeah, so actually we might be pulling off now with this big cell over here. We're pulling off better performance than possibly originally. So that's pretty good. Probably not the most exciting of things in the world, but you did get to see a little bit of this trial and error related to any of this engineering. When we think we can just pluck something from the shelf and make it work, this is usually why you want to get things like dev boards and test boards. I was close to being on the cusp of, do I need to build a little just boost board that has, tens of capacitors that I can install? And that still might happen because, it will be a very simple board. But there is a bit of trial and error to this. And while I was fortunate that between the choice of batteries, figuring out where current losses are, and figuring out and having those caps just on standby because they might not be in stock anymore, I was able to get to a point where we're actually able to achieve at least what I could see is standard derailleur performance. Now, the only other way I can figure that out is to take one of my bikes apart and I rip apart one of their V3 power units, and I don't want to do that. But given the current draw we saw, the power supply at 12 volt looked like it was handling it, and the voltage sag through the system was bigger than what we were getting with the boost circuit in the end, and gave us less than 1, maybe 2% increased shifting performance. But one of the other things that I need to test really is what happens when the voltage of that battery gets really low. So if I continue with this project, it's not going to really be commercial. Maybe I would sell the circuit boards and maybe pre-built if people wanted to do it, or kits or something. But basically, I wouldn't ever be selling this as a finished product. It's mainly a potential solution for all those dead or dying V3 power units out there. I've actually gotten, over the last 2 years, maybe 6 or 7 emails about is there a way to replace the battery in the power unit? They can't find a V3 power unit. They don't want, the V4 system was made incompatible intentionally, so they don't want to, people don't want to buy a full group set. And if they can't get the parts and they're no longer in warranty, well, this keeps kind of coming back to one of the things that I, even though I've made some mistakes with, I really think right to repair. And in this case, it's kind of guerrilla repair. And that's perfectly fine. So if there's a way to keep using this hardware, because I mean, a lot of it ergonomically, Campagnolo beats everyone for me personally. The shape of the shifters, the feel of the shifters, the layout of the shifters for the most part. It all kind of beats what I've seen out there. Like the Shimano stuff I really dislike. I don't like the ergo shape of the SRAM double tap system. They're kind of fatty Chungus boys, but I do like the double tap system. I'm not a big fan of the E-tap front derailleur shifting method with the both buttons. Don't really like that. So maybe that's part of me being an old fogey and a traditionalist. But anyway, yeah. This may be part one of multiple, or it may be part one of one. So keep following, and hopefully you enjoyed that and learned a little bit more about electronics development. It's not necessarily as easy as grabbing stuff off the shelf. So with that, take care.